So welcome to the ANOVA lesson, or the analysis of variance. Before I start, I just want to talk about a few definitions. So variation is a common word that just means differences. I use it a lot conceptually. It's an important concept for today's lecture. The differences among scores, the variation among scores. Variance is a specific word that means sum squares over degrees of freedom that you've been exposed to. Another word is systematic, which is due to known causes. So it's a synonym of signal and noise, right? Systematic is another word. So you can have systematic variation, systematic variance. They're similar, but variance is talking specifically about that calculation. And you have unsystematic, which is a word that means due to unknown causes. Synonym is noise, so signal and noise are present in this lecture. So today's most important concept is the goal of an ANOVA, and that's to parse variation or variance into systematic and unsystematic variation or variance. So it is parsing the variance into signal and noise, like I said earlier. So signal and noise is part of this statistic. Now, this lecture does rely on previous knowledge. So the first thing I need you to realize is that variance is sum squares divided by degrees of freedom. So remember that. Variance is also standard deviation squared. So that's the variance is the part that we take the square root of to find standard deviation. I also want you to remember, within a specific group, why do scores deviate from the group mean? Well, that's due to error. That's going to be important. Remember that. Those deviation scores within a group are due to error. They're not due to signal, they're due to error. And also remember, in a perfect experiment, every score equals the group mean. Because that's important too, because I'm going to foreshadow just a little bit that the mean is the part of the score that is due to systematic variation or signal. So keep that in mind. And then just ultimately, I'm going to say sums of squares. But I expect you to understand that that means summing the deviation scores squared, right? So deviation scored, you find that, you square it, then you add all those together. So I'm not going to go through that every single time because you already know how to do it. So let's look at a data set and let's begin to parse it into total variation, systematic variation, and unsystematic variation. Let's look at that and sort of get a feel for it. So when we look at this data set, a few things probably pop out. Number one, you see three different groups, right? The differences between those three groups are due to our experiment, and that's systematic variation. So we know that when we're finding that systematic variation, we're going to be looking at differences across those three groups. We're definitely going to get that. We also know that within each group, scores deviate from the mean due to error. We've already learned that. We've already talked about that, so we shouldn't focus on it too much, but we can see where the error is coming from. Within each group, that's error. Why do the numbers in the REO group, why are they different from each other? Why are they not all 2? Well, there's error in the data set. Why are the numbers in the Times New Roman group not all 5? The mean of that group, there's error in that data set. Why are the numbers in the Comic Sans group not all 8? Because there's error in the data set. So that's where our unsystematic variation is going to come from. We know there's systematic variation is going to be like, oh, why do the groups differ from each other? Why is the REO group's mean lower than the Times New Roman group's mean, lower than the Comic Sans group's mean, right? Like that's called systematic variation that we caused. And then if we're just looking at the whole thing, one big old unit, we ignore the groups, we ignore the variation within groups, we ignore the variation across groups, we just look at the variation as if these numbers were all part of one big data set with no definition. Just 1, 2, 3, 4, 5, 6, 7, 8, 9. And I did choose a simple data set so you can see the mathematical properties. Okay? So this is just thinking about it out loud. Let's see this in practice. So let's dive into our first component, total sums of squares. Remember, we're going for total variance, which is sum squares divided by degrees of freedom, so we got to do sum squares first. So in every sum squares requires some deviation component. So the scores in this case are all scores in the data set. The mean is the mean of all scores, which we call the grand mean. And just a reminder, this is how you calculate sum of squares. The sum of the deviation scores squared, right? Deviation score, square it, add those all together. Why do these scores vary from each other? Well, like we're looking at the total variation. Part of that variation is due to our manipulation. We did use different font types on a reading score. So, some of this variation is due to our manipulations. We call that systematic variation, systematic reasons. And, some of it we don't control. It's just due to error, unsystematic reasons. So right now we're not parsing the variation. We're just finding the total variation so we can figure out how much there is to parse. So when we're calculating the sum squares, we ignore our groupings, we ignore them, and I put a circle around that to represent this is one big data set that has a mean of 5. So in order to find our sum of squares, we have to calculate the deviation scores from 5, 1 minus 5, 2 minus 5, 3 minus 5, 4 minus 5, 5 minus 5, 6 minus 5, 7 minus 5, 8 minus 5, and 9 minus 5. We square them, right? And then we sum those squared scores together. We add all those squared scores together. And that's how we get our sums of squares total. It's not even that complicated. It's something that you already know how to do. And I just want you to see, our total variation is looking at the total data set as one big data set, ignoring our manipulations and calculating what we already know how to calculate, a variance, sum squares, essentially. And then we're going to calculate variance. Degrees of freedom is always difficult. It's a riddle. Now imagine that our mean stayed the same, but we didn't know what our original numbers were. We lost all those numbers, and all we knew is that all these numbers have to average to the same mean. How many of them are free to vary and how many of them are fixed, right? Well, let's just make it simple. I'm just going to choose 5 to represent my numbers. So that first green bar top left, that could be a 5. Okay, so that's free. Now I'm going underneath it now. The next bar underneath that, that's a 5 too. And the one under that, I'm going to say that's a 5 as well. So those first 3 numbers in the first row on the left are all 5. But I chose them to be 5. They could have been anything, so they're free to vary. And I can still do the math where the other numbers average to 5, no problem. What about I do the same thing for the next 3 numbers? I set them all to 5. Yep, they can all be set to 5. They're all free to vary. Okay? Now I go to the third column. I set that number to 5. I'm like, yes, I can still manipulate the last 2 numbers to make sure that the grand mean is still 5. So that one's free to vary. My next one's also free to vary. However, that last one has to be 5. So it's not free to vary. So all the numbers are 5, but that last one had to be 5. The other ones I randomly chose to be 5. I chose them to be 5 just to make the math easier for us, right? But you can see, that last number can't be 4, it can't be 3, it can't be 2, it can't be 1, right? Once the other numbers are picked, that last one is forced to be 5 as well. So our degrees of freedom here would be the total number of observations minus 1, and you can see that. Right? But you can work it out. You can work it out with the riddle. Okay, all these numbers have to average to the grand mean. That's 5. And so really, we have 9 numbers. We have 8 that are free to vary. So the total number of observations minus 1 is always your total degrees of freedom in an ANOVA problem. So our total variance, which is a number we don't use that often, but we did the math, sum squares divided by degrees of freedom, and its variance due to systematic and unsystematic factors. Let's move on. We got the total component figured out. Now, the within groups component, we call it within sums of squares. Within groups, within. So within groups has been shortened to within before I was born. So we call this the within sum squares. But if you really want to be particular, call it within groups. Because why do scores vary within groups? Well, you can see my answer here. It is due to unsystematic reasons, unsystematic variation. Not systematic, unsystematic, right? Error. We already know that though, because we've been calculating a version of within group sums of squares since we started talking about standard deviation. So when we're actually doing this specific sum squares calculation, the scores are all scores. However, the mean is the mean of each group. So we're actually using 3 different means to calculate our within sums of squares. It'll make more sense in a picture, but you already know this one. You know that, oh, scores in the REO group differ from each other due to error. Scores in the times group differed to each other due to error. And scores in our Comic Sans group differ from each other due to error. It's all error, unsystematic reasons. So this picture represents how we will calculate the sum squares within, or the sum squares that's due to unsystematic variation, or the sum squares that's due to error. So the first thing we do is we do it by group. So we take our first group, which was the REO group, right? Their group mean is 2. And so then we find our deviation scores: 1 minus 2, 2 minus 2, 3 minus 2. We square those, we add those together, and we hold them for right now. We do the same thing for our Times New Roman group. 4 minus 5, 5 minus 5, 6 minus 5. Clearly the group mean is 5, right? We square those deviations, we add those together, we hold them as well. And then finally, we do the same thing for our Comic Sans group: 7 minus 8, 8 minus 8, 9 minus 8. We square those and add those together. And that's how we find our sum squares within that group. Now, all of these are 3 different estimates of error, and we simply add them all together to find our within sum squares, the complete within group sum squares. So that might take a little bit to get your mind around, but essentially what we're doing are the sum squares calculations. We did the second day of class. We're doing it 3 times or more, 1 for each group, and we simply add those sum squares together. And that is our within sum squares. Now, within groups degrees of freedom, I've already talked about this once in this class, so this one also shouldn't be that surprising, but it's the same riddle. Oh, imagine we forgot all our original numbers, and all we knew is that our scores have to average to their group mean. So within our REO group, those first 2 scores, let's say they're both 2, right? Well, they were free to be anything, so they're free to be anything, right? But that last one is then forced to be 2. It can't be 3, it can't be 4, it can't be 5. So here with that riddle, how many of these observations in the REO group mean, that's the one on the far left, are free to be anything? Well, 2 of the 3, right? We asked the same question for the Times New Roman group, right? Let's say that first green box, what number could it be? Well, I'm just going to choose 5, but I could have chosen anything. That one's free to vary. The second number, it could be anything. It could be 1, it could be 7, but I'm going to say it's 5. So that's free to vary as well. That third mean is forced to be 5. It can't be 4, it can't be 2, it can't be 1. Or that third score can't be, anything but 5, because these 3 numbers have to average to 5. If the first 2 numbers are 5, the third number has to be 5. And finally, it's the same thing for our Comic Sans group. Like that first observation in there, I'm going to randomly choose 8. The second observation, I'm going to randomly choose 8. I could have chose 23 or 1,000. I decided to make my math kind of easy today. And then that last observation has to be 8, so that all the scores average to the group mean. So our within groups degrees of freedom here, within each group, it's the number of observations within each group minus 1, right? You can see that for the REO group. You can see it for the Times New Roman group, and you can see it for the Comic Sans group. But if you really want to think about it, it's the total number of observations minus the number of groups. You can clearly see that too, right here. But I want you to see that. I want you to see where the degrees of freedom are coming from, right? Remember, variance is sum squares divided by degrees of freedom. So now we have everything we have to calculate the variance, right? And so that's pretty good. But this sum squares and variance represents the sum squares and variance that's due to error, unsystematic variation, error, right? So we know total And now we know error. Well, if we think about that, why does that make sense? Because the numbers in the REO group differ from each other, not due to our manipulation, but due to individual differences and other factors we can't predict or measure, right? Same thing for the folks in the Times New Roman group. Why do those numbers differ from each other, right? Well, that's due to, error. Why do those numbers in that final Comic Sans group differ from each other? That's error as well. So sum squares, degrees of freedom, right? Within the within groups component, those numbers differ from each other because of error. So now we know the variance in our study that's due to error because sum squares divided by degrees of freedom. And remember, sum squares is simply the sum of, you take your deviation scores, square them. So it's the sum of those deviation scores squared, right? Deviation score, square it, add those all together. That's your sum squares, right? Degrees of freedom, you see where that's coming from here. And that's literally number of observations minus number of groups. But now you can see why. So the within variance is calculated by sum squares divided by degrees of freedom within. And this is variance due to unsystematic factors or error. Now, for between subject sum of squares, it's going to be a little bit complicated. So I want you to kind of get ready for that. I'm going to teach you something that most stats teachers don't teach, and I really wish they did. I think it'll make the process simpler. But it goes back to my point about the mean representing the score that's due to systematic variation. So let me talk about that a little bit more. Try not to get confused. But if you do, just kind of follow along and watch what I do. Okay, so why do scores vary from their group mean? This is the question for the previous aspect. We already know that. We know that scores vary from their group mean due to error. We know that score minus the mean is error. We know that. So, but we also know that scores are impacted by error and our treatments, our manipulation. So I want you to think about this. Score minus the mean equals error. Okay, so that deviation score within that group is due to error. So how do we figure out what part of the score is due to the manipulation? Well, I want you to go back. Remember that perfect data set when all scores when there is no error in a data set, all scores equal the group mean. So the mean represents the treatment effect in general. Like you can see that, like, oh, the difference between the three means represents the effectiveness of my manipulation. But in terms of the score itself, right, the mean also represents the part of the score, the individual scores that are due to our manipulation or treatment. So follow along with me there. Just realize this though, like, okay, the score minus the mean is error, right? The mean represents the part of the score that's due to our experiment. This is really important because the way I'm going to teach you how to calculate sums of squares is a lot more simpler than you've ever been taught before for between groups. So for the between group sums of squares, the scores are mean replace scores. So every single score matters, right? Like every single score adds variation to the data set. Every single score adds variance to the data set. So we don't want to just we don't want to ignore the fact that we have 9 scores and just look at 3 means, which is common practice in the way a lot of folks teach this. What we want to do is we want to replace every score with its mean. Because why? Because that score replaced with its mean is just simply representing that score in terms of systematic variation or variation created by the experiment. And then for our deviation score, right, like score minus a mean, the mean once again is the grand mean. So the deviation score that we're interested in is mean replaced scores minus the grand mean. So why do our group means differ, right? That's due to our experiment. That's due to systematic variation. So the between groups component, whether it's sum squares, degrees of freedom, represents the impact of our experiment, our treatment, our experimental manipulation, whatever you want to call it, on the scores. So let's see that in practice. So I have a data set now that is just score replaced means. So I have 2, 2, 2, 5, 5, 5, 8, 8, 8. What this is saying is like, oh, like I have 9 scores, and this data matrix right here represents pure systematic variation, or our best estimate of pure systematic variation. So, right? So it's almost like we get to construct that perfect data set. We're like, oh, well, this is just the data due to our systematic variation, due to our manipulation. So we replace each score with its mean, and then we simply do a very simple, very super simple calculation of sum squares. 2 minus 5, 2 minus 5, 2 minus 5, 5 minus 5, 5 minus 5, 5 minus 5, 8 minus 5, 8 minus 5, 8 minus 5. Those are our deviation scores. We square those deviation scores, right? So 2 minus 5, right, is negative 3 squared, 9. I'm not going to do that for every single one. We do all those squaring of those deviation scores. We sum all those squared deviation scores. That's our sum squares between. And this is a lot simpler than the way you have to deal with a formula. It's like, wait. Every single score is impacted by systematic variation or experiment, right? So the component of that score that is systematic variation is the mean. So we replace the scores with their means. And then we just calculate a very simple sums of squares calculation. It's super simple right here. I'm sorry. I hope you see that, but it is. It's super, super simple. Now, talking about degrees of freedom here is complicated. So I've left my original scores up before I've done the riddle to show you something. Like, if we look at it, outside of the riddle, all 3 of those scores in the REO group had to be the same, right? All 3 of those scores in the Times New Roman group have to be the same. All 3 of those scores in the Comic Sans group have to be the same. Now, they don't have to be 2, 5, and 8, but they do have to be the same. So what I know here is that 6 of these observations are not free to vary. I know that. And you can see that. You can see that those numbers aren't free to vary from each other. So those bottom 6 are not free to vary. So now, right, I've replaced those scores with the variables x, y, and z to represent, well, they could represent anything, right? But that first column, they all have to be whatever x is. The second column, they all have to be what y is. And the third column, they have to be what z is. So imagine that I said, okay, that x is 5. Okay, that could have been anything. You know, I randomly chose 5, so that one is free to vary. Now I'm doing the same thing for y. Y is also 5, but that could have been anything. I chose 5 to make my life easier, but it was still free to be anything, but I chose 5. That z has to be 5. In this data set, with that complicated way to look at it, there's only 2 degrees of freedom, which is the number of groups minus 1. But for me, when I do the math, it doesn't make sense when I use those fancy formulas that don't replace each score with a mean. Like, to me, that's like ignoring the fact that that their group means impact all 9 of these scores. So ultimately, this is how you find your between groups sums of squares and your between groups degrees of freedom. And remember, sum squares divided by degrees of freedom is variance. Between group variance is sum squares between divided by degrees of freedom between. And this is variance due to systematic factors, your experimental manipulations, your conditions, your experimental treatments. I really hope that made sense. You understand deviation scores. You understand squaring them to get rid of the zeros. And you understand summing them. That's sum of squares, right? Sum of squares divided by degrees of freedom is variance, and this is called the analysis of variance. So we'll get into that in a moment. But I want to focus on sum squares, because sum squares has some very interesting properties. So the total sum squares equals the between sum squares plus the within sum squares. So remember, between groups, that's the variation between my groups. If you want, my groups have different means, it's the variation between my group means, right? So ultimately, that's variation we caused with our experiments, or I caused with my experiment. That's our signal. That's our systematic variation. Within groups variation is variation I don't know where it came from. It's individual differences. It's unsystematic variation. It's crap. It's error. It's noise. It's junk, right? So the total variation is made up of systematic and unsystematic variation. There's no third source of variation. Okay, and for some squares, this works out. It doesn't work out for variance. The variance calculations don't sum up this nicely, and if you look at the math, you'll figure out why. But I want you to see this with the sum squares. But mostly what I'm trying to tune you into is like, oh, total, that's the variation of my whole data set. That's my numbers, how they vary from each other, from the grand mean. And that's due to systematic and unsystematic variation. Now, I know you've heard me talk about signal to noise. Signal to noise is everywhere in stats. And the between groups variation, the variation between our different groups, between our REO group, between our Comic Sans group, between our Times New Roman group, right? That's due to my manipulation. That's signal, right? And the variation within groups, the variation within the REO group, plus the variation within the Times New Roman group, plus the variation within the Comic Sans group, that's noise. The analysis of variance is signal variance over noise variance. And when I'm saying variance, I mean it very specifically here. Sum squares divided by degrees of freedom. So we have between groups variance divided by within groups variance. And I didn't put it here twice because I think you can realize that, right? That's our F statistic. That's the statistic we use in an analysis of variance. Yeah, and so really, that's the main thing. Oh, we just calculated this F statistic. That's another signal to noise ratio. Signal variance over error variance. So there's another signal to noise ratio statistic that's called eta squared. And just like the T statistic is a signal to noise ratio and the Cohen's D is a signal to noise ratio, well, here we have the F statistic is a specific signal to noise ratio, and the eta squared is another signal to noise ratio, and the eta squared is an effect size measure, just like Cohen's D is. So let me just talk about this for a little bit. Dividing by degrees of freedom is not uniform across between and within groups, right? If you look at it, what do the degrees of freedom tell you in the between groups setup? Well, it tells us the number of groups minus one, right? If we look at the degrees of freedom within groups, it's the total number of n minus the number of groups. These are hardly comparable, right? And it makes it hard for people to think in proportion, to really think about analysis of variance. It doesn't really make that much sense to those of us that like to think in percentages and proportions. You really can't think of proportion with variance, but you can with sums of squares, because remember, total sums of squares equals between plus within. So eta squared is the between sums of squares divided by the total sums of squares. So it's the percentage of total variance that you caused to happen. That's all it is. That's eta squared right there. Now, I am going to say that in the future, you're going to see me call this eta squared equals between divided by between plus within. And that's because stuff gets a little sticky when you have within groups designs. Let me show you that in the next slide. So let's look at what a within subjects design would look like. All I did was add 3 names to our previous existing data set. So I kept the data set exactly the same. We have 3 different participants instead of 9, and each of us participated in all 3 of the different conditions. So everything we talked about remains the same. The total variation remains the same. The between groups variation remains the same, and the within groups variation remains the same. Now, one of the things that you can see is if you look at this data set, you can see that my scores are lower than Aaron's, and Aaron's scores are lower than Ashley's. That's actually really kind of cool, right? Because now we're actually able to answer, well, why do scores differ from their within group means? Well, I can actually pinpoint this to individual differences. And so this is what you get when you have a within subjects design. You get a new component, the within subjects component. So let me just give you some overview on within subjects design and get right to it. So within subjects design, I want to remind you within groups has nothing to do with within subjects. Within subjects has the same participant in all conditions. That's one version of it. Or related participants, maybe triplets, right, in each condition. When we're calculating the components, nothing changes for total, between, or within. That's all the same. We just have a new component now called the subjects component. And let me show you how we would calculate that. So when we're calculating our subject sum squares, the scores are subject mean replace scores. Now subject mean would be, I'm in this data set, so it's my mean across all the different conditions. So me being me impacted all my scores, right? So that's important. Like, so what was my average score across the three conditions? That's the me being me. So we're going to replace each of my scores in the three conditions with my subject mean. We're going to do the same things for my friends Aaron and Ashley. Okay, now here's what I want to say. Because I was present in every group, I was in the Ario group, I was in the Times New Roman group, I was in the Comic Sans group, my subject mean cannot impact the between subjects variation, variance, or sum squares or any of that. So my being me impacted, it's an individual difference, right? It's going to impact the variation within groups. So that's where it's really going to matter. And I'll explain to you what we do with this, but my subject mean helps explain why scores varied within each group, right? So does Aaron's subjects mean, so does Ashley's subject mean, right? Because these are individual differences. What I can now do is I can account for individual differences and I can remove them from what I thought was error, right? This is a special type of systematic error. It's systematic error that I don't really care about except for removing it. Let me go through the process and it'll make a little bit more sense. So I have color-coded the different participants, myself, Aaron, and Ashley, to just give you a visual here. Now I've replaced all of my scores with my average score, which is 4. I replaced all of Aaron's scores with her average score, which was 5. And I replaced all of Ashley's scores with her average score, which was 6. And so now all I have to do is calculate my sum squares. 4 minus 5, right, to get a deviation score. 5 minus 5 deviation score. 6 minus 5 deviation score. 4 minus 5 deviation score. 5 minus 5 deviation score. 6 minus 5, right? 4 minus 5. 5 minus 5. 6 minus 5. Those are all my deviation scores. I square those, right? After I square them, I add them all together. And that is my sum squares that is due to participants per subjects, right? And that's really as easy as it is. It's very similar to the other form of systematic variation, the variation between groups, where I replaced all the scores with the mean of each group. But now I'm looking at it in terms of finding the systematic variation that's due to different people in the different conditions. So my scores were lower than Aaron's, and Aaron's were lower than Ashley's. And so ultimately, that's how we find our sum square subjects. We're going to ask how to find our degrees of freedom subjects next. Now, in terms of degrees of freedom, we had a very similar problem as we had before. Remember, I replaced all of my scores with my average score. So that means all my scores have to be the same number. I just called it the variable x. Right? All Aaron's scores have to be the same number, and all Ashley's scores have to be the same number as well. So what I know there is that those whole second and third rows, those are not free to vary because they have to be set to the same number as is in the first row. So that's not freedom to vary. That's a forced thing. They're forced to vary. Now, let's do the same thing with those first 3 numbers. So that x, that green x by my name, let's say that was a 5. I freely chose that to be a 5 to make my life easier, right? I did the same thing for y. I chose that to be a 5 as well. They could have been any number. They could have been 23 or 900 or 8 billion, but I chose 5. And then that means that z next to Ashley is forced to be a 5 as well. right? Using the riddle, using the thought process, we can see where the degrees of freedom are coming from. We can see what they mean. We get a feeling for what they are. And what you can see here is that it is the number of subjects minus 1. But it gets a little, once you start breaking it down into means and doing these sum of squares and degrees of freedom calculations by like looking at the subject average and forgetting that there are individual scores. There are 3 scores that are impacted by me being me. There are 3 scores impacted by Aaron being Aaron, and there's 3 scores impacted by Ashley being Ashley. Now, we get this, our sum squares and our degrees of freedom, and you're like, well, what do we do with it? And I'll show you that in the next slide. So when it comes to our sum squares and degrees of freedom, we still have a similar relationship. Total sum squares equals between sum squares plus within sum squares. Between equals variation I caused with my experiment, systematic variation or signal, and within equals variation I did not cause with my experiment, which is now due to 2 factors, error and subjects or individual differences. So we can't calculate the error sums of squares directly in the ways we've been doing the other calculations, setting up the sum squares calculation. All we do is we take our within sum squares minus our subject sum squares, and that gives us our error sum squares. And that's the only way to do it. We're looking for variance, so that's sum squares divided by degrees of freedom. So we have to get our error degrees of freedom, and that's just the within degrees of freedom minus the subject's degrees of freedom. So that's another subtraction factor. And then clearly our error variance is error sum squares divided by error degrees of freedom. We are still interested in the signal to noise ratio. Our between component still represents signal. Now, our error component represents noise, and our error component is just the within minus the subject's component. So when we're doing our analysis of variance, it's signal variance over noise variance. That's our F statistic, and our F statistic is going to be the between groups variance divided by the error variance. And this is only for within subjects designs because you can remove that subject's component from the within component. So with our partial eta squared, we're trying to figure out the percentage of variation that we caused to happen with our manipulation. And before we did that by the between sum squares divided by the total sum squares. Now, if we look at our total sum squares, it includes, between, right, the variation we caused to happen. It includes error, random error, variation that we don't know where it's coming from. And it includes, subjects, error, or individual differences. We know where the individual differences are coming from. And so it really doesn't make sense to include that in our denominator, right? Because we want to know the total percentage of variation that matters that we caused to happen. Well, individual differences, we measured them, we got rid of them, they don't matter anymore. So we call it partial eta squared. It's still telling us the percentage of variation that we caused to happen. It's just removing individual differences from the total. So when we look at that, partial eta squared is the between subject sums of squares divided by between subject sums of squares plus error sums of squares. It wouldn't make sense to hurt ourselves by including the participant or individual difference sums of squares, the subject sums of squares, because that's variation that we don't care about, right? It doesn't matter. We know where it's coming from. And so we've accounted for it. We've parsed it, and it's individuals are different. We removed that. So now of the stuff that matters, the between, like the variation we caused and the variation we didn't cause, right, that we don't know where it's coming from, right? What percentage of that did we cause to happen with our experiment? And by percentage, I mean proportion. Proportion times 100 is percentage, and that's the best way to think about partial eta squared. Multiply it by 100, think about it like a percentage. Okay, so this is the data set you're going to use. It's basically the same one I used, except instead of 1, 2, 3, it's 2, 4, 6, 8, 10, 12. That's also pretty easy to deal with. Let me show you the homework on the next page, the questions I'm going to ask you about this data. So what do you have to do for homework? I'd like you to show me where the sum squares total, sum squares between, sum squares within, sum squared subjects is coming from by showing me which scores are being subtracted from which mean or means. Now, in most cases, it's just a set of scores being subtracted from a mean. That's true for total, that's true for between, that's true for subjects. But you got to be careful with within, because that's scores within groups. So there's 3 means being used to calculate deviation scores. So within the ARIO group, within the Times New Roman group, and within the Comic Sans group. I'd like you to compute degrees of freedom total, degrees of freedom between, degrees of freedom within, degrees of freedom subjects, and degrees of freedom error. Now, by computed, I'm not giving you a formula, right? Look at how I found them earlier. So, use the riddle. You can figure it out. But ultimately, there were some pretty simple formulas to remember. Degrees of freedom total is the total number of observations minus 1. Degrees of freedom between is the number of groups minus 1, so the number of experimental groups. Degrees of freedom subjects is the number of participants minus 1. Degrees of freedom within is a little bit more complicated. It's total minus the number of groups. And then degrees of freedom error is going to be degrees of freedom within minus degrees of freedom subjects. So there you go. Calculate those. Shouldn't be too hard now. I've given you these little formulas if you need them. We also learned about 2 really cool statistics today. One's a signal-to-noise ratio called the F ratio, or the F statistic. So how would you calculate the F ratio? The variance what? So it's going to be something like between, within, total, error, divided by variance between, within, total, or error. You got to pick the right one. How would you calculate partial eta squared for this problem? So this is sum squares what divided by divided by 2 other sums of squares. Tell me what they are. Now there's 2 other sums of squares here because it's a within subject's design. You have the same participants completing the experiment. But ultimately, we're trying to figure out the percentage of total variation that matters that we made happen with our manipulation. Just a quick summary for you. Between subjects' designs, different participants or animals in different conditions, we have the total sum squares equals the between sum squares plus the within sum squares. Our F ratio is variance between divided by variance within systematic variance divided by unsystematic variance. It's signal-to-noise ratio. Eta squared equals between sums of squares divided by total sum squares, the percentage of variation we caused to happen with our experiment. Within subjects' design is same or related or matched participants or animals in every condition. So total sum squares equals between sum squares plus within sum squares. But within now equals error sum squares plus subject sum squares. The F ratio is variance between divided by variance error, which is systematic variance divided by unsystematic variance. We've removed the individual differences. That is systematic variance, but it's systematic variance we don't care about. And partial eta squared is the percentage of total variation that we caused to happen with our manipulation, but we also remove individual differences because we know where they're coming from. It's systematic variance due to individual differences. It's not due to error. It's not due to our treatment effect. We took care of it. We removed it. We did what we were supposed to do, so it's gone. This is just your review. Enjoy. You can handle this problem.